Questions about anything from last time or anything? I think I might have written that down last time before my notes crashed. Anyway, that formula right there is the Poisson formula for just a random disk. I had done it carefully for the unit disk. And if you know it for the unit disk, you actually can do a very simple thing, namely doing a change of variables just by scaling the distance and translating the origin. You can get a Poisson formula with zero work that way for any old disk of radius capital R about a point z naught. And the formula looks very similar. It's the law of cosines again that gives you that denominator, and it just pops right out. Of course, you could start from scratch and do it the way I did it, using separation of variables, but that would be a lot of work, and you don't have to do it that way. Anyway, that formula, when you apply it to the center, shows you that u at z naught, let's say that would be the case where little r would be 0, and so a lot of that stuff would go away, and you would see that u at z naught is the average, 1 over 2 pi times the integral of u around the outer circle. That's the averaging property. So harmonic functions satisfy the averaging property. That's a fascinating thing. And the theorem I'm going to do today, which is one of the beautiful theorems in the subject, is that the averaging property implies the function is harmonic. So let's see, to say it, a continuous function, of course it's a real valued function, so it's important to assume that it's a continuous function and that satisfies the averaging property. Meaning the averaging on any disk inside the region where it's defined gives the value at the center, on any circle, I should say. So if it satisfies the averaging property, it's harmonic. And that's kind of an exclamation kind of thing, because being harmonic involves Laplacian and derivatives. And if we just start with a continuous function, you don't even know if it's differentiable. So the averaging property, I drew this picture last time, is I've got a blob, so I'll call that blob omega. F is continuous on that blob. And if I take a little circle here about a point in there, let's say a point about z naught, and that'll be a circle of radius little r, then the fact is that u at z naught is 1 over 2 pi times the integral from 0 to 2 pi. And I like to use complex notation here rather than polar coordinates centered at z naught. In complex notation, that would be z naught plus r e to the it dt. So I like to think of that as a temperature function. The average temperature, the temperature at the center, is the average on all circles. Steady state temperatures do that. One of the key ideas in the proof is we've seen that the averaging property implies the maximum principle. So we've seen that the averaging property implies the maximum principle, namely that the maximum occurs on the boundary. So that's going to be the key idea. But here's another clever. That's the key idea, and here's a clever idea. Let's restrict attention to a disk. To a disk. Let's make it a disk of radius capital R about z naught, and let's say the closure is contained in my region where my function is continuous and satisfies the averaging property. Okay, and I'm going to let I'm going to define capital U of z to be equal to Poisson integral formula, the one I just wrote up there, the Poisson integral of the boundary values of my little u. So not capital U, but little u, of little u on the circle of radius capital R about z naught. Okay, what do we know about capital U? We showed last time that capital U is harmonic. Let's see, we know it's continuous on the closure on the closed disk all the way up to the boundary, and has the prescribed boundary values that we wanted it to have. Namely, capital U of z naught plus re to the it on the circle is equal to my little u. And finally, capital U is harmonic on the inside, meaning it satisfies the Laplace equation. Inside the disk of radius capital R about z naught. And so it satisfies the averaging property there too. Inside dr2 dr. Okay, so now the brilliant observation is that, okay, well, little u minus capital U satisfies the averaging property. So that's the aha moment. Little u minus capital U satisfies the averaging property and is continuous up to the boundary. And it's 0 on the boundary. Averaging property. Sorry. Skipped a word. Is continuous up to the circle. And is 0 there. And now you remember my proof of the averaging of the maximum principle. So the picture for the proof of the maximum principle. Remember when I had a circle? There's a circle. And let's say the maximum happened at this point right here, A. The max at A. Well, remember, then I use the averaging property. So that would be the maximum on the whole closed disk. Happens at A. And then I would use the maximum principle and make these circles expand until they just barely touch the boundary. One more maybe. Now on that last circle, by the way, by continuity and uniform continuity, the averaging property would hold on that last circle too, that just barely touches internally tangent to the circle. And remember, I'm averaging something that's less than or equal to m on that circle. And so that would be less than or equal to m times 2 pi and 1 over 2 pi in front. That's the biggest that integral can be. And my calculus lemma said the only way that could give me that maximum thing was if the continuous function on that circle was always m. So we'll say max, let's make it a max of m at A. And then we conclude by the calculus lemma is that the function equals m there too. So that showed that the maximum is attained on the boundary. Well, in the case of our function u minus u twiddle, u capital U, that maximum is 0. U minus capital U, that max on the boundary is a big fat 0. So that means that we've concluded from using this maximum principle we conclude that U minus capital U is less than or equal to 0 on the inside too. Okay, and I used U minus U capital U. I could have done the same thing for U minus capital U minus U. So I can just repeat the idea, repeat the argument, using capital U minus U in place of U minus capital U. And when you do that, you see that capital U minus U is also less than or equal to 0, because it satisfies the averaging property and is 0 on the boundary. So we conclude that U is identically equal to U in the disk. And this disk was randomly chosen. And because little u is equal to the capital U, which is a harmonic function, that shows that little u was actually differentiable and satisfies the Laplace equation. So that's the aha moment. Little u is harmonic. And by the way, last time we showed you can differentiate under the Poisson integral formula as many times as you want. And so, in fact, u is C infinity smooth. So we know that harmonic functions are C infinity smooth. And consequently, I started out with continuous, and now I've shown that it's C infinity smooth. On that disk. which isn't an open set. And so that shows, since I chose that thing arbitrarily, was arbitrary, we see that little u is harmonic on the whole omega, on the whole blob. That's all there is to it. That's a very sneaky little trick, and it gets used a lot in the subject of harmonic analysis. You want to show that something's harmonic and nice, you take it to be the Poisson integral of, and then you show that, oh, it's equal to its Poisson integral by some maximum principle or some other sneaky little trick. There's several little tricks that are wonderful that spit that kind of thing out, usually involving the maximum principle. Any questions about that? That's a beautiful thing, I think. It's so easy. Maybe I'll give a long-winded description of it, but it's a very simple idea. Two things. Well, I thought it'd be worth saying how important the Green's theorem is, because this is the place in mathematical analysis that it was invented for. So the importance of Green's theorem. And I thought it would be a good idea to start out with a demonstration of Green's theorem for the unit disk, because that's the basic idea of the whole thing. So there's a thing called Green's theorem, which is one thing, and then there's another thing called Green's identities. There's three of them, which are all related to Green's theorem. So I want to do it first for, it's important to emphasize that Green's theorem is easy and very elementary. It's just a fundamental theorem of calculus on the unit disk. It's just the fundamental theorem of calculus, basically. The freshman calculus version. Okay, so let me draw a picture here. I'm going to have the unit disk parametrized in the counterclockwise sense. There it is. And the Green's theorem is that the integral around, this is C, the unit disk, integral of C, p dx plus q dy is the integral over the solid part of dq dx minus dp dy. And that's with respect to area, dx dy. Okay, you probably learned that in Math 261. And you might have actually seen this proof I'm about to show you in the case of the disk, which is pretty elementary. So, let me review what those symbols mean. Let's parameterize C by the curve parameterized by x of t, y of t. And I'll let t go from A to B. Actually, the most obvious thing to do here would be to have it x of t would be cosine t, y of t would be sine of t. So an example of such a thing as t ranged from 0 to 2 pi. That would be a natural thing to do. But it doesn't really matter what we do. The integral around c of p dx plus q dy is a shorthand thing for the integral as the parameter goes from a to b. We would have p along the curve. That would p of x of t, y of t. And dx is shorthand notation for dx dt dt. So that'd be x, I like to call that x dot of t dt. Okay, so you think of this as representing dx dt dt. And that, when you cancel the dx's, dt's, is shorthand dx. That's how people remember what that symbol means. And of course, the q one be the same thing, plus the integral from a to b of q of x of t, y of t. And now dy represents y dot of t dt. Okay. Now I'm going to look at my curve now. I'm going to split my curve into two pieces. A top piece, which I'll make be blue. I'll call that C sub top. And a bottom piece, which I'll make green. Also counterclockwise. I'll call that C sub bottom. And there's -1 and there's +1. Let's see how I'm gonna parameterize this now. I'll let my C sub bottom, that's an easy one, so I'll write it down. C sub bottom is going to be parameterized by x of t is going to be t. So that means the t is going to start at -1 and go to t, and go to +1. And the y of t is, let's see, that's the bottom of the thing. So y of t is going to be minus the square root of 1 minus t squared. That's the graph of the unit circle, the bottom half. Okay, and C of t is going counterclockwise. So it would have to start at the +1 and go to the -1. So it's going to be convenient for me to take it backwards. So minus C of t, that would start at -1 and go to +1. So that would, I would still do with x of t is t. But now the y of t is going to be the plus square root. That's the top. Okay, and what, once again, the t is going to go from -1 to +1 because I'm going the other way on that one. Okay, I claim now that the integral around the whole curve of p dx is the part of the Green's formula that is the double integral of dp dy. Let's see, it's going to be minus this, minus dp dy dx dy. Okay, let's see it now. Let's just do it. That the integral around c would be equal to the integral around the bottom, half, plus the integral around the top half. And that would be equal to the integral around the bottom minus integral around minus the top. So that one is good. But this is going to be minus the integral along minus C of t. Okay, and that's equal to the integral from minus 1 to 1 of p of t, and there's that square root thing. I'll call that the function h bottom of t. That's the minus the square root of thing. And let's see, x prime of t is 1 times dt. That's because x prime of t is equal to 1. Because x of t was equal to t. Okay, and so that's that. And then the other one would be minus integral from minus 1 to plus 1 of p of t, h top of t. And we get also 1 dt here. Okay. And you look at that for a second and said, well, how the heck would that be related to a partial derivative in the y variable? And that's when I was saying that this is just the fundamental theorem of calculus. So if you think about a little vertical thing going from the top to the bottom, so I would take a little vertical thing like this, and think about integrating like this dt. And use the fundamental theorem of calculus. So that's the picture I'm thinking of. So this is where you draw that picture and start thinking about how the heck you're going to relate these things. This is the integral from minus 1 to 1 of let's see, this thing right here, I'm going to shove it under one thing. This is p of t, h, I'm going to put a minus out front. Then I can change the order here and start with h top. H top of t minus h bottom of t. And I'm integrating that to dt. Now I'm going to change the t to an x because I want to make this a double integral. So right now I'm going to change the t to an x. It's just a dummy variable. And so when I do that, I get minus the integral from minus 1 to plus 1 of p of x, h top of x, minus p of x, h bottom of x. dx. And now if you just took Math 261, it wouldn't take very long for you to think of this. I can think of this as an instance of the fundamental theorem of calculus in the y variable. So let's see what that would be. That would be the integral from the bottom curve to the top curve of dp dy of x, y, dy. Do you agree? That's that little orange thing. X would be like the middle of that little orange vertical slice. And that thing right there is like the dx is the element of the base area. And those would be dy's, would be the little things I cut up into little boxes there. And when you look at that from the point of view of Math 261, that's an area integral. So it's an area integral along, it's minus the integral with respect to area along the inside of dp dy dy. So check. All I did was use the fundamental theorem and sort of the basic facts about integration over an area. Questions about that? I don't know if everybody sees that in sophomore calculus or not, but it's the way you make people believe Green's theorem. That's the vertical half. That's my favorite half. But the other half of Green's theorem now, I'll blast over it. It's the same, except now instead of doing top to bottom, you have to go left to right. So this time I would take, I'd call this side C sub left, and then my green side, let's say I wanted to go counterclockwise. So this would be C sub right, and now this would be y equals minus 1 to y equals plus 1. And I'd parameterize, let's see, C sub right, I'd parameterize by, this time y of t would be t, as I go from minus 1 to plus 1. And the x of t now, on the right, would be plus the square root of 1 minus t squared. And on the left side, I want to have a similar thing that I can combine, so I want the t to also go from minus 1 to plus 1, so I'll parameterize minus c sub l. That would start at the bottom and go to the top. And then I could parameterize the y of t the same. That's going to make dy dt be 1, by the way. That's nice. That makes those integrals really simple to write out. And the bottom would be, the left would be minus the square root of 1 minus t squared. And now when you do the calculation, you'd have the integral around c of q dy. That's the other piece of the Green's theorem. That would be the integral. I'd do this, the right half, and then I'd do minus the integral along the left, minus left half of q dy. That would be the integral from minus 1 to 1 of q. Let's see, I need to call it, I'll call it g right of t, comma t. And then I'd have minus g, q of g left of t. Last time I called it h. This time I'm calling left and right the g functions. Then I'd change that one to x, like I did before, and this time I'd get integral from minus 1 to 1. And when I use the fundamental theorem of calculus, I'd get integral from g sub, let's see, the bottom is g sub left, so so g sub left of, I'll change it to x, and g right of x. And this time it would be this time I'm doing a fundamental theorem of calculus, and it would be the d by dx derivative. So this would be dq by dx. and dx. And I'm integrating that with respect to the dt is going to be dy. So this time I'm going to change the t to a y, since it's a dummy variable. So I guess I should put, yeah, so I have x, y is being fixed in that thing. That's the t, and it's the x's that I'm using the fundamental theorem on. So I see I screwed up here. These are y's. Because the t, think of the t as the y. Anyway, it's exactly the same idea. It's just left to right instead of up to bottom to top. And that takes care of the other half of Green's theorem. And the fascinating thing is you can do the same thing on any region bounded by a curve that has a top and a bottom and a left and a right. You can do the same proof when your region is bounded by a curve, and there's lots of those. With a top and a bottom and a left and a right. So an example, of course the example probably where you saw the proof in sophomore calculus, rectangles have that property. There's a bottom curve and a top curve and a left curve and a right curve. But a fascinating thing to do is if you want to do a Green's theorem for something that has a hole in it, cut out a hole, I can do something clever here. I can take cuts like that. And I'm going to think about the top curve as going around counterclockwise. And the bottom curve, and the middle thing is going around clockwise. Okay. And then when I think about those cuts I put in there, when I do it around this first quadrant one, I'm going to go down that curve and then go follow the real axis like this. That makes that counterclockwise. Then when I go into the next quadrant, I think about counterclockwise, and I'd be going the other way on the purple one, but the same thing on the blue. And when I get here, I'd have to go this way to make it counterclockwise. And on the next one, to make it counterclockwise, my arrow would go the other way, but I'd still go counterclockwise on the outer circle, come back this way, and then go clockwise on the inner circle, like I've been doing. And finally, on the last one, to go counterclockwise, I'd go this way and then this way. And each one of those things has this property that it's got a top and a bottom and a left and a right. So each quadrant curve has the top, bottom, left, right property. left-right property. So I could do Green's theorem on each of those, and it would be perfectly elementary, just a fundamental theorem of calculus, and you believe it. And when you look at it and add them all up, the fantastic thing is the purple cuts cancel. Purple cut integrals cancel when you add them up. You add up all four of them. And so you get a Green's theorem for an annulus, which is a pretty interesting thing. This is how you're going to show the averaging property using Green's theorem. So Green's theorem for an annulus. I'll draw the picture. The outside annulus goes counterclockwise. The inside annulus goes clockwise. And the region I'm doing integrating over is this. So I'll call that omega. I'll call this C sub big radius and the inner one C sub little radius. Actually, I kind of like to call it minus C sub radius so that my outer one is counterclockwise and my inner one is clockwise. So that would make them C sub r and C sub little r both counterclockwise with that notation. Yeah, I'm going to stick with that. No, I'm not. Sorry. Sorry about that. I changed my mind. Here's what I'm going to do to make it clear, I hope. So when you add those four things up, you get the integral around the outside minus the integral around the inner one of p dx plus q dy equals the integral over the area region of dq dx minus dp dy with respect to area, dx dy. And it's just a matter of adding up the four Green's theorems around those quadrants. And there's a way of remembering that fact that the outer one has to go counterclockwise and the inner one has to go clockwise. That's called an orientation. And let's see, if I followed my nose along this tangential direction, then the outer normal would be poking out to the right of my tangent vector as I crawl around that thing. So if I'm crawling around that curve, I'd stick out my right arm, that's pointing outside the domain. And if I crawl around the inner curve and stuck out my right arm, same thing. So the normal vector, the outward pointing normal vector, is to the right of the tangent vector. That's how you remember what those orientations are. If you have a domain with a whole bunch of holes, you'd use the same principle and the same idea of cutting it up into pieces. So that's an orientation. Fancy word for it. The outward pointing normal vector is to the right as you stick out your right arm and crawl around the thing to the right of the tangent vector. in the direction of the yeah. But I gave you a very elementary proof of that fact for the annulus. And so to use Green's theorem to see the averaging property, we're going to use a Green's identity and shrink that inner annulet, that inner circle, down to the center, like we did when we proved the Cauchy integral formula. It's going to be just like that. Oh, sorry, that was my other class. It's going to be just like that thing I did in my other class. And they're very, very related. So when you get comfortable with this, you'll get comfortable with doing this kind of argument again and again. It pops up all over the place. See, I'm kind of running out of time. I have one more easy thing to say. Another important theorem in this subject is the divergence theorem. So Green's theorem implies the two-dimensional divergence theorem. In fact, they're exactly the same theorem when you really get down to it. Okay, and the divergence theorem is the integral around the outer circle of force field dot normal vector ds equals the integral around the inside of the divergence of that field dx dy with respect to area. If you're in physics, you might call that grad dot f. Okay, and the force field, I'm thinking it as a F1 times the I direction plus F2 times the J direction. And the divergence of F is dF1 dx1 plus dF2 dx2. And if I wrote that down for you, I'm going to show you why that's Green's theorem. I'm going to claim, I don't want to rush through it now, but these two things are exactly the same thing. If I choose the P and the Q to be the right thing, this would just be, it would be clear that these are the same, absolutely the same thing. And I think I'll do that next time rather than try to rush through it right now. Any last minute questions about anything? Yeah.
I mentioned for Green's theorem, you need to have the boundary of the region to be what you're going to talk about. Are you able to take?
Oh, you don't have to have that. In fact, the big question, that's a really ugly proof that's sort of unsatisfying. And, you know, the early proofs, obviously Green thought about that way. He did it mainly for disks and things like that. But he realized, you know, if you know it for things that you have a top and a bottom and a left and right, you can hook them together in clever ways. I mean, I could draw you a convex thing. It'd be convex, and I said, how would I make it be, have left and right and top and bottoms? That would have one. This would have one. Yeah, I could think of a way to cut this up so I could use that really simple thing, and that was unsatisfying. So there's a famous book by Spivak called Calculus on Manifolds,